In this video, we're going to cover section 8.6 on catalytic hydrogenation. This is another addition reaction that has synthetic utility as well as industrial utility, as it's commonly used in the food industry. Now, catalytic hydrogenation involves the addition of hydrogen, molecular hydrogen, H2, across a double bond. And this is often done in the presence of a metal catalyst. Hence, the reason why we refer to this as catalytic hydrogenation as opposed to just simply hydrogenation. Now, when an alkene undergoes catalytic hydrogenation, the transformation that occurs is it becomes a alkane. So we're undergoing a transformation from an alkene to an alkane as a result of forming two new bonds to two hydrogen atoms. So as you can see in this example, we have a alkene in the presence of hydrogen gas and platinum as our catalyst. This is our metal catalyst. The observed product resulting from this reaction is the alkane. And so what's not shown in the bond line structure is that we're forming two new bonds, two hydrogen, for those two carbons of the original alkene. So again, this reaction is carried out by treating the alkene with hydrogen gas and a metal catalyst. And this is often carried out under higher pressures than normal atmospheric pressure. So it could be a few atmospheres of hydrogen gas as opposed to just ambient normal pressures, 1 atmosphere. So under higher pressure in the presence of, there's a variety of catalysts, metal sources that can be used. Platinum is common, palladium is common, and so is nickel. And in this particular example, we don't see any chiral centers being formed as a result of this hydrogenation. And so stereospecificity in this particular example is irrelevant. But we'll see an example where stereochemistry or stereochemical products are produced. Now this figure describes in a relative way what the effect of a catalyst is on the reaction pathway. And you can see that the main effect is that we're lowering the activation energy of the reaction when a catalyst is present, as opposed to when it is absent. So the net result is that the rate of the reaction will be increased due to that lowering of the activation energy. So in the absence of a catalyst, hydrogenation will require extreme pressures and potentially elevated temperatures to be successful. But the catalyst lowers the external conditions that are required for this reaction to occur. So let's look at the mechanism for catalytic hydrogenation. Now, like we saw for hydroboration oxidation and oxymercation demercation, we looked at certain aspects of the mechanism, but we didn't look at every detail. And that's the same for catalytic hydrogenation. We're going to give you a general sense of what's occurring at the surface of these metals with the hydrogen gas and the alkene, but we're not going to look at the arrow pushing patterns for these reactions, as they generally involve radical systems. So from a general perspective, we can treat the metal surface in this way, where we have these metallic atoms neighboring one another in some type of crystal lattice. And when you're carrying out these hydrogenation reactions, typically what is happening is that we're passivating the surface, or we're covering the surface with hydrogen. And H2 is administered as a gas, and when it reaches the metallic surface, you're going to have dissociation of those diatomic molecules, H2, into individual bonds between the metal surface and a hydrogen atom. So once the surface has been covered with these hydrogen atoms, then the alkene is also introduced. And when the alkene is introduced, it's going to form an association, an interaction with the metallic surface as well. But it's more of a physisorbed absorption initially, and then you see from the physisorbed interaction, we have this chemisorb event. So there's a chemical reaction between the alkene and the metal surface. So the pi electrons of the alkene will interact with that metal surface, forming a covalent system. Now, it's at that point that we have individual hydrogen atoms forming new bonds with that alkene. And you can see that in the first step, we see this association of one of the carbon atoms with the metal surface, and at the same time that's happening, the other carbon is going to pick up a hydrogen from the metal surface. And then with time, this bond will break and be replaced with a new carbon-hydrogen bond. And it's at that point that there's no longer that strong association with the newly formed product, the alkane with the metal surface. And so then it will, basically leave that surface. So this is, again, just a general look at how this occurs, but it happens in a stepwise manner. And like I said, most likely involves radicals in the formation of these new carbon-hydrogen bonds. But I wanted to give you a sense using this image as to what's happening at the nanoscale. In addition, it's important to kind of think about these reactions in this way because it helps to describe why we see syn addition. We're getting both of these new covalent bonds are both being formed from the same face or same side of that original alkene. So we observe syn addition in the products that are formed from catalytic hydrogenation. And that's more clearly observed when you have, as in this case, a system that has multiple chiral centers. And so if you have two new chirality centers being formed, as shown here, we have a chiral center here and a chiral center here. When two new chirality centers are formed, we would expect, if there wasn't any preference for syn or anti, that we would end up with 4 different structures, 4 enantiomers. But in fact, what we observe experimentally is only 2 of those 4. And this is similar to what we saw for hydroboration oxidation, that we see 2 enantiomers, a pair of enantiomers, in which they are both obtained through a syn addition process. So syn addition will give you, as shown here, 2 hydrogens are adding and at the back, whereas the hydrogens that added to this structure are facing towards us. So we'll obtain 2 enantiomers from that catalytic hydrogenation process. So overall, this table summarizes what we would expect from a stereochemical standpoint, depending on the number of chiral centers that are formed during the reaction. So if there are no chiral centers formed, as we saw in that previous example, then it's really this syn requirement is not relevant. We're only going to form one particular product. If one chirality center is formed during the process, then we'll see both possible enantiomers are formed. So hydrogen can add again from either side, depending on how that alkene approached the metal surface. And if there are 2 chiral centers formed, as we saw in this top example here, we're only going to observe the products resulting from syn addition. So a pair of enantiomers will be formed. Now, just as in closing this particular video, I'd like to comment on the fact that catalytic hydrogenation is used quite often in the food industry. It's used to prepare partially hydrogenated fats and oils. And so one example, obviously the oils that are used to create our Mickey D's and Dirty Bird foods. But the reason why they're oils at room temperature is that we're partially hydrogenating some of these seed oils so that they'll solidify at room temperature as opposed to being a liquid. So margarine is the common example, that it's spreadable on your morning breakfast, and that's because it's been partially hydrogenated such that there's a stronger interaction between the fats and oils, the triglycerides, such that they solidify, they pack and solidify at much lower temperatures. If they can't pack so well, then they're generally liquids at room temperature. And that helps to preserve the shelf life of products as well. And so there is a cost analysis or benefit to that. But as you know, there also have been issues with the use of partially hydrogenated foods or processes in the production of foods. And the primary issue has been the formation of trans fats. So as you can see in this figure, naturally occurring fats and oils, they're generally a mixture of compounds referred to as triglycerides. And that's given by the fact that you have these 3 alkenyl chains. So we have pretty much almost a fully saturated chain, but you can see there's some unsaturation. There's an alkene present in these tails of the triglycerides. Now, the natural form, the most common form produced biosynthetically, is the cis isomer of triglycerides. Now, when we undergo a catalytic hydrogenation of these systems, it is possible that you don't get complete reaction. You don't get the reaction going to completion, meaning that although we will undergo hydrogenation of some of the tails in these fats, you can see in this example that what's left behind is a trans isomer in one of those chains. And this is the distinction between your cis fats and your trans fats. And the trans fats, because they are not biosynthesized, they're synthesized through a chemical process, it's believed that, and there's strong evidence to support the fact that these fats are not good for us. So these trans fats, they are believed to cause an increase in your low-density lipoprotein, and these LDLs are not the good cholesterol. They're considered the bad cholesterol. It's the HDLs, the high-density ones, that we wish to consume. And so as a result, there has been a correlation drawn between the consumption of trans fats and that of disease, specifically cardiovascular diseases. So it's important as a consumer to read the labels and to ensure that you're not consuming large amounts of these partially hydrogenated foods, especially those that contain discernible amounts of trans fats. So if you have any questions about catalytic hydrogenation, by all means, send me an email. Thank you.